Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were examining how the different parameters of this equivalent circuit of the single phase induction motor are impacted by the rotor angle. And of course the rotor angle is the integral of the rotor speed. So the idea of this is, as I already said, is to bring in the mechanical component into our electrical model, which so far seems to be completely independent of the movement of the machine, because remember, this is a mechanical system. This is a motor which is going to rotate, and therefore if we have to completely model this motor, we must also bring in the movement into our equations. So therefore this is what we've been doing, and we have looked at three parameters, that is the stator resistance, the rotor resistance, and the stator inductance, and we found out that all these three were independent of the rotor angle. So it doesn't matter how the rotor moves, doesn't matter where it rotates, and doesn't matter which position the rotor is. For a squirrel cage cylindrical rotor induction motor, these three parameters are independent of the rotor angle. If we have a salient pole rotor, in that case we found that the stator inductance does depend on the rotor angle. However, since we are considering to begin with a cylindrical rotor induction motor, because we are looking at squirrel cage induction motors, we have concluded that the stator inductance is independent of theta m. So now the next question is, what happens to the rotor inductance, that is LR, and this way we will look at each and every parameter. So as always, before I start the lecture, a little bit of brief background, that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can access on my own webpage, which is pythonpowerelectronics.com. So this is the home page, and if you click on the button Learn, it will take you to the list of courses. So as of now, I have 5 courses. The very first course is Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about the basics of how you can use Python and packages such as the signal package within SciPy to analyze and design filters for power engineering applications. The third course is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power electronic applications, with the specific example of a single phase inverter connected to a single phase grid. And the last course I have is called Why Specialize in Power Electronics, and this is a free course which is targeted towards either high school students or junior undergraduates, so that they choose power electronics as their domain and specialization. And this course talks about some of the challenges and opportunities available in power electronics. So all these courses are available on 2 platforms, which is Udemy and Decibels Labs. If you click on any of these buttons, it will take you to the link of the course. So the link for this page is provided in the description of this video. If you're interested, please do check it out. With this, I'll get back to my lecture. So in this lecture, I'm going to talk about how the rotor inductance is impacted by the rotor angle. And to do so, let's go back to our flux diagram, which we used for the stator inductance, or rather to determine how the stator inductance is impacted by the rotor angle. So I will go back to the Inkscape diagram which I drew before. So in this diagram, I had considered the stator, which are these 2 outer concentric circles, which is the stator. And of course for this we can just go over to Chrome and check out what we were looking at, that is this one. So basically I was taking a cross section of the stator, which means that the 2 outer circles are the stator. Right? So the stator winding is basically wound around the circumference of the stator, and the rotor is this squirrel cage, which is basically a cylindrical rotor with bars which are short circuited on either ends. For our simplicity, we have assumed the stator to be just 2 slots diametrically opposite each other, where the coil is wound around these slots. Of course, this is a simplification, because typically you would wind the stator windings all around the stator, not just in one, not just in these two slots diametrically opposite each other, but for the sake of analysis, this is good enough. Similarly, the rotor can also be considered as just two concentric bars, or rather just two large bars diametrically opposite each other, so that it appears as if it's just one coil with so many number of turns, right? So this is exactly what this diagram shows. It shows these two concentric circles, which is the stator, and it shows these two slots, which are the two stator slots between which the stator coil is wound. And here the inner circle is the rotor, and these two slots, or rather these two bars, can be said to be the rotor slots where the rotor winding is wound. Or you can even assume that this is just several rotor bars at the same location diametrically opposite each other. Now here, of course, we were looking at the flux which is produced by the stator, which means we are assuming a current flowing in the stator coil. So we had assumed that the current flows into the page in this upper slot and comes out of the page in this lower slot. So we had said that therefore, by using right hand thumb rule, we say that the magnetic flux lines are concentric circles which are in the clockwise direction for this upper slot and the counterclockwise direction for this lower slot. Now, we had neglected any current flowing in the rotor because we were looking at that time at the stator self-inductance. That is, the flux produced by the stator which links with the stator due to the current flowing in the stator. That is the definition of self-inductance. That is, what is the flux which links a coil due to the current flowing in the coil itself. Now, we are going to repeat some of this discussion, but now assuming that a current is flowing in the rotor and we're going to neglect the current flowing in the stator. So for that, let me copy over this. And let me paste it here. And let me just move it. So it's basically the same diagram, but here I'm going to edit it. And I'm going to delete some of these because I don't need the stator flux anymore. What I need is the rotor flux. So we are now back to the same thing. That is, we have the stator slots, we have the rotor, and we have the rotor slots, right? And this is the rotor axis. Now the question is, if I were to assume a current flowing in the rotor coils, how will that be? To be able to draw the flux diagram, we need to assume a direction of current just the way we did for a stator. So we can assume anything. For example, we can say that the current flowing into this slot or this bar or this collection, whichever you wish to say it, goes into the page in this slot and it comes out of the page in this slot. Okay? This is just an example. You can reverse it, not a problem. But now that we have this assumption, we can draw the flux lines. As with this case, we know that whenever a current flows in any conductor, the magnetic flux lines are concentric to the conductor and the direction can be found using the right hand thumb rule. So first, let's just draw with freehand some diagrams, which is a flux diagrams. So there will be some which are just leaking into the air, but most of them will be linking with the stator. If you have better softwares, you can use them to actually map out the flux lines. This is just to give you an approximate idea of how the flux looks. And I'll draw the same for here as well. So now the direction is, we use the right hand thumb rule, and I've already said that here the current flows into the page, and therefore flows into the page, we have to grab this conductor with our right hand in the direction, the thumb pointing in the direction of the current, which means that here the flux lines will be in the clockwise direction, right? And of course, in this case, the flux lines will be in the counterclockwise direction because the current is flowing in the reverse direction, right? So now that we have these two, The next question is, what happens, or rather first let me draw a straight line that indicates the horizontal line, because we need to know the direction that this rotor makes with the x-axis. Right? So this is that angle. So all I'm saying is we know the rotor angle, we know the horizontal axis, and therefore we can say that at any point of time, the angle made by this rotor axis with the horizontal axis is the rotor angle theta m. Right? That's how it works. Theta m is equal to omega integral of omega t. So as it moves, it will make a changing. The angle made by this rotor axis with respect to the horizontal axis will keep on changing. So in order to be able to decide how this flux is changing with respect to the rotor angle, what I'm going to do is I'm going to select this entire object and group it. So now that we've grouped it, we can rotate it in any direction. So let's say, for example, it has rotated by 90 degrees. Let's assume that the direction of rotation of this rotor was in the counterclockwise direction. If it is in the counterclockwise direction, as time increases, this rotor angle will increase. So let us assume it is rotated by 90 degrees, in which this is a new rotor angle. Now the question here is, and this new rotor angle, what has changed with respect to the previous case? And if we were to compare by just flipping it back, we see that the difference is the same. There is no difference, just as the case with the stator. So let's say, for example, this flux path. Just as the case with the stator, we can divide the flux path into different segments. For example, there is a path of the flux through the rotor, which is a magnetic material, typically laminated iron. There is a flux path through the air, and there is another flux path through the stator. In some cases, there is leakage. For example, this is a case of leakage. Why? Because the flux produced by the rotor is only through the air and does not link the stator. So this is not going to do any useful work. So here there are only two segments, through the rotor and through the air. But in most other cases, there are three segments: through the rotor, through the air, and through the stator. Just as we did with the case of a stator, we can make an approximation. We say that because the flux flowing through the magnetic material is flowing through a low permeability path as compared to the air, because remember, permeability of iron is 1000 times more than the permeability of air. Therefore, the reluctance of air is 1000 times greater than that of iron. So, the reluctance of this flux path is primarily the reluctance of these two paths in the air. The reluctance through the iron is negligible, and we can neglect it. So the next question then arises is, how do we determine the length of this air gap, or rather the length of this path through the air? Now, this diagram is probably not very good because, as I said, I'm drawing freehand drawings, but flux, just like current, just like water, just like anything, will always flow through the path of least reluctance, which means that it will always flow through the path which has the lowest reluctance. So if we try to look at what might be the length of this air gap, the length of, if this flux through the air gap passes through the radius, right? If it passes through the radius, then in that case, this length of the air gap is the minimum. Alright, and you can verify this yourself. If you take a piece of paper and draw several lines along the radii and you draw other lengths, you will find that the length through the radius is always the minimum. Therefore, a vast majority of this flux will actually flow along the radii. And therefore, we know that this flux is the length of the air gap is the length of this radius, or rather the difference between the radii of these circles. That is, this is the air gap. So now that we have this, the question here is, if I were to again rotate it, has that changed? And the answer to that is, no, it has not. For the simple reason that if we have a cylindrical rotor and we have a cylindrical stator. Stator is typically always cylindrical. The rotor, if the rotor is also cylindrical, then this air gap is the same. And if the air gap is the same and we are neglecting the path through the iron because it is a low reluctance path, then in that case the reluctance of this flux path does not change whichever position it is. How much ever I flip it, it's always going to be the same. And therefore, if we come to this conclusion that it's always going to be the same, then in that case, whichever position the rotor attains, the flux produced by the rotor that links with the rotor will always be the same. And this comes back to the basic definition of inductance. As we said, inductance is the flux linkage of a coil with respect to the current flowing through the coil. Since we are talking about the self-inductance and the self-inductance of the rotor, this is the flux linking the rotor due to the current flowing through the rotor. And if this flux linking with the rotor is not going to change, then the rotor inductance is also not going to change. So therefore, we can say here, we can add here saying that also the rotor inductance is also independent of theta. So far all these parameters are independent of theta. Now, just before we conclude this, we can also ask the question, what happens if we have a salient pole rotor? Now, you might be quick to jump to the conclusion that if it's a salient pole rotor, then in that case, they should be, that is, the rotor inductance should be dependent on the rotor angle. But I would encourage you to take a salient pole rotor and draw these flux lines and confirm for yourself, and you'll find that actually the rotor inductance does not change. And we can look at it in the next video next week. But with this, I'm going to end this lecture. We have now concluded that for a squirrel cage induction motor, the stator resistance, rotor resistance, stator inductance and rotor inductance are independent of the rotor angle. What now remains is the mutual inductance. Right? Now, as you can obviously guess, for this to be a machine model, something has to be dependent on the rotor angle, and this mutual inductance will be dependent on the rotor angle. But to determine this, let us again draw the flux lines just like we did for the case of this stator inductance and rotor inductance. And this will come in probably 2 lectures, because maybe next lecture I'm going to talk about salient pole induction motor and how the salient pole induction motor, this rotor inductance, quite surprisingly, is independent of the rotor angle. So with this, I'm going to end this lecture. If you have any doubts, please do either comment or send me a message on social media or send me an email, whichever is your preference. Otherwise, I will see you next week, where we will talk about salient pole induction motors and how the rotor inductance is impacted by the rotor angle. Thank you so much for watching, and see you soon. Goodbye for now.